Recording is rolling. It is Tuesday, March 25th. So you guys remember yesterday, I introduced a whole new topic to you guys. Electricity, circuits, how does current work? Now, this is a big topic. There's a bunch of new variables. There's a bunch of new ways of thinking about things. So I need to do a recap with you guys. I never quite got to Joule's law even yesterday. So I need to show you guys that. We'll do a little bit of Kirchhoff's rule. Okay, and then I gave you guys as you're walking in, this page has a bunch of circuits set up on it. So we'll look at how do you set up resistors in parallel and series, and how does the current flow. Okay. On the back side, there's some more of these, got some tables for you guys, so we'll do some of that. And what I'm trying to work towards is, I want to get you guys a lab when I can. So here's a lab page that I have these printed, ready to go. I have you guys draw some different circuits and use this multimeter to measure what's the voltage and what's the current at different points in your circuit. Right. So we're working towards this. Now, how this is paced out today, I wanted to get to the lab tomorrow, but I don't think we'll quite have time for it. So I'll do a review with you guys today and a few new things, and then we'll do some examples, and then we'll probably have to do some more examples tomorrow, and then I want to get you guys this lab as soon as I can. But before all that, leading into this, I got two guys painting a fence. Do you guys see Alan and Bob here? Okay. By the way, the reason I'm asking you this question is because the math to solve this particular question is exactly the math to solve resistors in parallel when you see them. They got Alan and Bob. It takes Alan 3 hours to paint a fence all by himself. He can paint this whole fence, take him 3 hours. Now Bob, let's say it takes him 4 hours to paint the whole fence by himself. Right? Now they're going to make a two-man team. Now we got Alan and Bob, and they're both painting the fence in parallel, so at the same time. So you got two paintbrushes. Right? Now just make for sure you know what's going on. I'll tell you what this is not. This is not, oh, there's only one paintbrush, and Alan's going to do some work, and then he's going to hand the paintbrush over to Bob, and then Bob makes it. No. That would be in series, like sequential. That is not. They both have paintbrushes, and they're both painting the fence at the same time. Right? So Alan 3 hours by himself, Bob 3 hours by himself, or sorry, Bob 4 hours by himself. So how long does it take them to paint the fence together? Okay? Now I've had a couple of students today actually be able to answer this question. So I'm wondering, can any of you guys figure out how to solve this, or know what the answer is? I wouldn't really expect you to know how to solve this. I was kind of surprised. I've had a couple students know how to solve this earlier today. Okay, but how about this? Even if you don't know exactly how to solve it, maybe you could sort of frame boundary conditions for what the possible answers could be. Okay? For example, there are some really tough math puzzles out there that like people with PhDs in math don't know how to solve. Like nobody knows how to solve. But they can say, well, I know it can't be less than this or more than this because we can kind of prove that. Okay? So how about this? What if I change this a little bit? What if it's two Allens, like Alan and Alan, like Alan and an Alan clone? How long would it take two Allens to paint the fence? 1.5 hours. How long would it take two Bobs to paint the fence? 2 hours. Do you guys see that? Because it'd just be like 4 hours and 4 hours, but they paint them together, it would take them 2. Right? So now if we're back to one Alan and one Bob, does it make sense the answer has to be somewhere between 1.5 and 2 hours? Right, that would make sense, right? So we got some boundary conditions on this anyway. So it's somewhere between 1.5 and 2. Okay, so I'll show you guys, there's actually a couple of different ways to solve this. So I'll start with the fraction method. So you guys ready for some notes? Okay. So 1 over the total time is 1 over Alan's time plus 1 over Bob's time. Okay. Okay, so I'll do 1 over the total is, now for Alan, that was 3 hours. And for Bob, that was 4 hours. So notice I'm setting up these fractions, right? Because what's the common denominator of 3 and 4? 12. So multiply this by 4 over 4. Multiply this by 3 over 3. So 1 over the total looks like 4 plus 3 over 4 times 3. Right? 1 over the total is 7 over 12. So wouldn't the total time be the reciprocal? Like 12 over 7? I didn't write units, but you guys know this would be hours at this point, right? Okay. And let's get a decimal on that. What is 12 over 7? That's like 1.71 hours. Hey, that is between 1.5 and 2 hours. It sure is. Right? We said the boundary conditions have to be somewhere between 1.5 and 2 hours. 1.71 hours. Right? That makes sense. Okay. All right, you guys all right with that? Okay. Now, there's a shortcut as long as you only have 2 people painting the fence, which is well, you can kind of see how this works with like 3 and 4. You guys see it's going to be well, 1 over the total would be the sum over the product. So as a shortcut, here, right shortcut right over here. Okay. The total time is the product over the sum. So that would be again 4 times 3 over 4 plus 3, which is 12 over 7, which is same things before, right? Like if you were sitting down and solving a bunch of these with lots of pairs of friends, you kind of stumble upon that eventually. Say, okay, well, it's got to be a product over sum. Okay, right, you guys that? Right. But again, that only works for 2 friends. Now, the product over sum method. So let me specify that in the notes too, right? If only 2 in parallel. I'll say in parallel because they're painting in parallel, but later on this is going to turn out to be resistors in parallel. Okay, then you can do product over sum. Okay. Right, everybody go with that? How about this? Let's expand this a little bit. What if we brought in a 3rd friend, Chad? So now Chad's going to help him paint. Do you think 1 over the total time could be 1 over Alan plus 1 over Bob plus 1 over Chad? Can we do that? Yeah. What if we bring in Derek and Eric and Ferric? And just like keep going. What if there's like 50 friends? Could you keep doing plus 1 over, plus 1 over, plus 1 over? Do that? Yeah, you could have like 50 people painting this fence, and you could just solve it this way, right? But see if you guys are following with what I said. Could you do this? You say, oh, well, the total time with Chad could I do Alan times Bob times Chad over Alan plus Bob plus Chad? Can I do that? No, it's not going to work. Okay, so this does not simplify to this. Okay, now so if you have lots of friends, if you have more than 2 friends, you can always do the fraction method. That'll always work. Okay. If you only have 2 friends, it's perfectly fine to do product over sum. Okay, you guys got that? Again, this is going to connect to resistors in parallel. All right, so everybody good with painting a fence? All right, so if in the next couple of weeks, if I ever say 2 guys painting a fence, I'm talking about working in parallel, and then that's the math to solve that. Okay. All right, so let's do some review, and then work our way towards Joule's law, which I never quite got to yesterday. Also, a little bit. All right, so what we got here? We got a bunch of new variables and units. So a point charge could be measured in coulombs. Let's say if I take that balloon and rub it against my hair, it charges it up. Now, if you get that charge flowing at some rate, some number of coulombs per second, like flowing along a wire, we'll call that 1 ampere, and that's going to quantify how much electric current. So current is quantified in amperes, which is like coulombs per second. Right, guys good? Now, why would current flow at all? There has to be some potential difference, and that's also called a voltage. So here, potential difference or voltage, right, measured in volts. Right, guys, how many volts is this boxy looking battery right here? Be like 9 volts. Yeah. Yesterday, Paul Hewitt had a 12-volt car battery. This little AA is 1.5 volts. I also have a cell phone charger. I'm gonna light up some stuff later. Actually, I can do it right here. Right. The cell phone charger is at 5 volts, so I should be able to light up these lights. There they go. Okay, light up these lights. Okay, got 12 volts. Or sorry, 5 volts on this charger. Okay. So maybe some battery and 1 volt. It's like energy per charge, so joules per coulomb, right? Oh, these Christmas lights I was just breaking out could be resistors. Resistance could be measured in ohms. It's Greek letter omega for ohms. Okay? And then finally, the last thing you want to care about is power in watts, which is one you actually know from last semester. You guys remember power in watts? 1 watt is 1 joule per second. So it's a rate of energy transfer. You guys remember that? Okay. Let's not worry about these green ones so much, but definitely the yellow part of this table. Okay. All right. So here's electric field on a point charge, right? KQ over distance squared, distance away from the point charge. Right. If you have 2 point charges, there could be electric force between them. Right? So KQQ over D squared. Here's what the K is, electrostatic constant. Right? Looks kind of like universal gravitation, kind of like that. Right? You can have, wait, is this the right order? Okay. I'll just go with it. Lots of things you can put on a circuit. Like I got some breadboards here. I'll show you guys breadboard later, but I got a bunch of load resistor pinned in here. So lots of ways you can rig up lots of little circuits, lots of things you put on this. For the next couple of weeks, mostly going to focus on these two. So voltage source, so think a battery, and a resistor. So think a light bulb. Yeah. So mostly care about those. Okay. There's what it looks like inside a battery. There's some battery chemistry that could sit on a shelf for years and have some potential difference between those two materials. Breadboard. So I got some breadboards here. Now, if you flip over this breadboard, well, can't really see what's going on behind the scenes, but here you can. And when I put these breadboards in your guys' hands a couple of days from now, I think I want to get you guys this lab if I can. I'll give you guys some breadboards and some resistors and some LEDs. I'll also give you guys some Christmas lights because I've been trying to use the multimeter to measure with the breadboard, but I've been having some trouble with that. But I know the Christmas lights definitely work, so I'll give it all to you, and you can see what you can do with that. But if you want to put together some circuits with the breadboards, you have to know what's going on behind the scenes. So these 5 dots in this row are connected by this metal strip, and then these 5 and these 5 and these 5. Right, so you guys see all these rows of metal. Okay. There's also a couple of rails or buses that go along the entire outside edge that connect all along here. Okay? If you know that, then you know how to connect these together. So for example, here I'll use this as an example. Right, here I got a resistor, right, and I'll play off my picture here. If I plug in this resistor in a way that bridges this gap from here to here, it's like here, here, like so like that, then whatever current goes through is going to be forced to go across this resistor, and it's going to light up the bulb. Wouldn't that be true? Okay. But let me show you guys something that would not work. What if I plug it in like here and here? You see that? Okay. Now that will never light up anything because that'll be all along the same metal strip. So all the electricity is just going to go along this metal strip. It's called a short, and it'll never go through the bulb, and it'll never turn the bulb on. So here I got something rigged up that I got some LEDs here, so you can definitely see it'll turn on. Okay. Get this electricity to there it goes. You guys see these light up? Got a red and a green bulb. Okay. And every single one of these is bridging a gap from one metal strip to another. Same thing here. I have, I'll just point this out. I got 3 in series here. I have 3 in parallel here. And I have a hybrid setup down here. Okay, so different setups, breadboard. Now, when I learned this back in high school, this only really clicked and made sense to me when I learned this analogy. So when you hear voltage, think of like pressure. So a battery is kind of like a pump. It's trying to push electricity through a circuit, right? Kind of like water flowing through a pipe system, right? There has to be some reason the water would flow, some kind of pressure difference, right? The current that flows, think of it like a flow rate, like cubic meters per second, something like that, right? And resistance, I'm thinking like a cross-sectional area from this pipe, right? And this actually turns out to be a really good analogy because, say, like when we get to Joule's law, like power and stuff, right? If you actually plug in the analogous variables, it creates a perfectly valid equation for Newtonian physics also, for like fluids flowing through pipes. So it works great, right? Also, all this stuff we're learning about circuits, I know it's taken us a while because it's a big new topic. You can apply this to traffic flowing through a city or set up a pipe system. So it applies to this kind of thinking too, right? And so here's a basic schematic for a flashlight. Right, flashlight, got voltage source, battery, resistor, light bulb, and a little switch there, on-off switch. Remove them. There it is. That's flashlight. Okay. All right. So I got this multimeter. I used this a little bit yesterday, and I'll use this a little bit later today. But I want to remind you guys how this works. So because when I'm up here, like later on today, near the end of class, I'll be rigging these up and measuring voltages and currents. So when we get there, right, it might be kind of hard to see what's going on. So when you're measuring voltage, you have to connect the leads in parallel because you're measuring a potential difference. Yeah, you guys see that potential difference? Say like across this resistor. Okay, so there's going to be some current that flows through, but the voltmeter is measuring what's the voltage drop across this resistor, and then you connect it this way. If I want to measure what's the voltage drop across the battery, I can measure it like this. Actually, here, I can do a real fast one. Let me pop this out, pop it over here, watch this toggle, measure volts. Let's do this 9-volt battery. Let's see if it's showing. Oh, get that glare off. There you guys. There it goes. Okay. See if it's right. There it is, 9 volts. You guys see 9 volts? Okay. And what I just did, and I'll save the battery there, okay, is I connected it, bam, like that right there, where it's like in parallel, right? But if you want to switch over and measure something different, current, you have to make some changes. I have to move this toggle over, switch this over here, right, which I'll do later today. Okay. You have to break open the circuit and force the current to flow through the multimeter, which is different. You guys see that? So I'll call that connecting series. And so we'll do some of those later. And then eventually you guys are gonna each have these multimeters and get to try that yourselves too. All right. If you're connecting resistors in series, so one after another, which is this right here. So like if I connect end to end, it's as if it's a single giant resistor. All you do very simply is what? Add them up, right? Because if this was 1 ohm and 1 ohm and 1 ohm, what's the total resistance? 3. 1 and 1, 1 was 3. So. But if you connect them together like rungs of a ladder, you guys remember yesterday that Paul Hewitt video, he did this near the end of class, I think the last like 10 minutes of class, right? Connect them like rungs of a ladder. That's in parallel. You see how, like if you trace around, the current would be forced to split and go one way or the other way, right? See, that's different than, see, in series, it was just a one-way street. There was only one way, all the current had to go through all three. But in parallel, the current splits, right? Now the total equivalent resistance, ooh, where have you guys seen this math? This guy's painting a fence. Ah, 1 over Alan plus 1 over Bob plus 1 over Chad plus Eric, and Ferric. Again, if you only have 2, you're allowed to do product over sum. Now, if you have 3 like this, and you want to use the product over sum method, you can do 2 at a time. So I could do it this way. I could do A times B over A plus B, like in terms of ohms, however many ohms they are, right? And then I could write that number down and treat that as a single giant resistor. And then afterward, I could bring in resistor C and do a new product over sum. Right, so we'll do some practice with those over next couple days. All right. Now, how much current actually flows? Here's Ohm's law. So the current is directly proportional to the voltage and inversely proportional to the resistance. So, guys, what if I double the voltage? If I double the voltage, what happens to the current? It also doubles. What if you double the resistance? What happens to the current? It's half as much. You see that? So there's Ohm's law. Right? All right, now, right, you guys ready for something new? Right. What I never quite got to yesterday was this one, Joule's law, which says power. You guys, what's power measured in again? Watts. Power in watts. You guys know that from last semester, right? So this may maybe like how fast is the battery being drained, if it's hooked up to a battery, right? What's the rate of energy transfer? You're allowed to go current times voltage, right? Or either one of these. They all tell you the same answer. Right. Let me show you guys that that's true. You can substitute in Ohm's law. So let's start with current times voltage. So if that's true, guys, could current be voltage over resistance? That could be okay, right? From Ohm's law. What if I substitute in for this I, V over R? Can you guys see that? I got a V over R right here from Ohm's law. Right. What is V over R times V? What is that? V squared over R. That's this one right here. Right. Or how about this? Could I rearrange Ohm's law into a non-fraction form? What if you cross multiply the R? Could V be equal to I times R? And I could replace this V right here with I times R. Because what is I times R? I squared R. There you go. So there's power in terms of current and voltage, current and resistance, or voltage and resistance. And any of those three might be more convenient to use to solve depending on the question that you get. So it depends on the setup and sometimes the geometry of the circuit. It's like, oh, it's easier to use that one rather than that one. Right? All right, so you guys good with Joule's law? Right. We're going to apply this later today. Right. And I got one more for you guys. And this one's a little bit involved. It's going to take me a few minutes to go through this one. So is everybody full focus up here? Is everybody paying full attention? Right. So let's get into Kirchhoff's rules. Now, Kirchhoff's rules tell you exactly how the current flows throughout a circuit if you're digging into the circuit. Okay? So now really there's only 2 rules, and I labeled them here, the loop rule and the junction rule. But a consequence of these rules, these other rules kind of fall out of these, so I just put them all on this page. And this you can figure out exactly what's going on inside any of these circuits that we do. Okay? So, and I got 2 basic circuits set up. I got a series circuit, the electricity goes all through one and the other sequentially. Okay? And I got a parallel circuit where, see, the current has to split. Is that? So let's start from the top and work our way down. So first rule, this loop rule. Now, this really applies to any loop. And the series example actually is a loop, isn't it? Okay. This says the sum of the voltages across any loop always zeroes out. So, for example, say I got a 9-volt battery. Let's put this 9-volt battery right there. You see? Because this would be the battery on schematic, right? Battery. Okay. 9 volts. Okay. If this is 9 volts, Suppose 3 volts drop down across resistor A. How many volts drop down across resistor B? If it's up 9, down 3, down what? What would cause it to zero out? So up 9. If this is down 3, this must be down what? Huh? 6. Yeah, 6. Guys, is it true? Up 9, down 3, down 6. Up 9, down 3, down 6. Wouldn't that zero out? You see that? Okay. Here's you guys a different visualization that I have not shown you guys yet. You guys ready for something new? Okay. Let's look at this waterfall analogy. Hey, look, it's resistors in series all over again. So remember I've been telling you guys that voltage is kind of like pressure, right? Another way to sort of think of that is like a height of a cliff, because like the deeper the dam, the more the pressure at the bottom, right? So I got this battery, which is like a pump, right? So if I'm taking this water and I'm pumping it up the cliff height, and maybe there's a little voltage drop, or I should say a height drop across this waterfall, a high drop here and a high drop here. Of course, these all stand for like, voltage drops, right? Guys, what do the voltage drops of the waterfalls have to add up to? The voltage supplied by the battery to begin with, right? You guys see if you start at some elevation and you work your way all around the loop, you have to have the same elevation as you started with. Yeah, that's the loop rule. That's it. That's the loop rule. You guys see the loop rule? It's good. Okay. Now this is true if they're in series, so they're all in series here. Okay. Series here. Okay. Right. So that's that one. But you could also apply this loop rule to, ooh, I see a loop right here. Okay. So what if I take my 9-volt battery, put it right there? Okay. Guys, if this jumps up 9 volts, how many volts does it jump down across this resistor? 9. Because it would be up 9, down 9, up 9, down 9. You guys see that? Okay. Or, ooh, look, do you see another loop on the, how about the outside perimeter? This is up 9. How many down is it right here? Down 9. Yeah. You guys see up 9, down 9, up 9, down 9. You guys see that? Okay. And show you guys the waterfall analogy visualization of that. Right. Now, of course, I have 3 here instead of 2 in parallel, but same idea. Right. Ooh, guys, if this pumps up 9 meters, wouldn't each of these waterfalls be 9 meters down? Yeah, up 9, down 9, up 9, down 9. Guess that? That's the loop rule also applies to a parallel setup. Okay. Which is exactly what this line says right here. This is the loop rule as it applies to a parallel setup. Okay. Notice that is regardless of the individual resistances. Guys, what if one of these resistors, I'm looking at the parallel setup, is like 1 ohm and the other is like 100 ohms? 1 ohm versus 100 ohms. Do they still have the same voltage drop? Yep, they sure do. Right? Now, on the waterfall analogy, that might be like a little skinny waterfall next to a really thick waterfall, but they can still have the same height drop, right? Sure. Right. What else do I have to say about voltage? Okay, I got one more row about voltage. Now, this one's a little more involved. Right, you guys ready to? All right, here we go. So this row right here says in this series setup, how does the voltage drop across each individual resistor? And what this fraction says is that the voltage drop, say across resistor A, is very simply proportional to the resistor A. So here, I'll throw some numbers at you guys. Suppose these resistors were 1 ohm and 2 ohm. You guys see that? 1 ohm and 2 ohms, right? For a total of 3 ohms. Okay. I'm going to bring in my 9-volt battery right there. Okay. So, guys, what is 1 divided by 1 plus 2? Is that a third? What is a third of 9 volts? 3 volts. Okay. Now, if you go over to resistor B, suppose I swap out these subscripts, put B, B. Okay. What is 2 divided by 1 plus 2? That'd be 2/3. What's 2/3 of 9 volts? 6. Okay. So if I have 1 ohm and 2 ohms, do you see it's gonna go up 9 volts and then down 3 volts and down 6 volts? And that would also satisfy the loop rule again, wouldn't it? Is that? Okay. All right, so you guys good so far with all the voltages? So far the rules we covered. We covered the loop rule, which connects to this right here, and also this right here. We showed exactly how the voltage drops down. We talked about all the voltages here. You guys good with all the voltages? Okay. Now let's switch over to current. Right, you guys ready for current? Okay. So in a series setup, the current, you guys know I is current. The current is very simply the same everywhere, again, regardless of the individual resistors. You can have 1 ohm and 2 ohms, you can have 1 ohm and 100 ohms. The current is still the same. And on the waterfall analogy, what that means is it's the same gallons per minute everywhere. It doesn't matter if these waterfalls have different heights or whatever. No, it's the same flow rate across the entire circuit, right? As long as they're all in series, right? Or the traffic analogy is if so many cars leave this parking garage and drive around, all the cars have to go through this stop sign, and also all the cars have to go through this stop sign. So the current's the same everywhere. Okay, guess that? Because current's kind of analogous to traffic flow. All right. So you guys good with that one? Now let's sit down this junction rule. This junction rule right here tells how the current splits in a parallel setup. Because if it's parallel, they would definitely do this junction, and the current would have to split. Okay. Oh, or sorry, actually, I'm kind of getting into this one, but here. The junction rule says that the current has to add up, has to equate. Right? So this actually satisfies conservation of charge, is what it is. Okay. So suppose you have 9 amps leave this battery. I'm just making something up. 9 amps. And it splits, and 6 amps go along this street. Well, guys, if there's 9 amps altogether and 6 amps cut this way, how many amps are left to go this way? 3. Yeah. So 9 could be the 6 plus this 3. Right? If you have 9 cars leave this garage and 6 cars go through that stoplight, the other 3 cars went through this stoplight. Right? And then they all meet up together and they form together. And now you have 6 amps plus 3 amps brings you back to the original 9 amps, and that goes through the battery. Right, so that's basically what this says. Okay, guys good so far? Because there's one more row to go. And it's this very last one. Now, this last one is the most involved. Right? It does make sense, but I do have to point this out, and you have to think about this a little bit. Do you guys see that the current that goes along branch A is proportional to the resistor B? The subscripts are backwards. You see it? Right? Now, it does make sense when you think about it. Because what if resistor A was like 1 ohm and resistor B is 2 ohms? On the traffic analogy, that's kind of like if this street has 1 stop sign and this street has 2 stop signs. Now, if you leave this garage and you're driving around town and you got to get back to the garage, then when you hit this junction and you look to the left, you see 1 stop sign. You look to the right and see 2 stop signs. Which way are you probably going to take? Probably the 1 stop sign. In fact, do you think most of the traffic is going to go along the 1 stop sign? Suppose there's 9 cars. Do you think most of the cars are going to go through 1 stop sign? Yeah. Right. But after a while, if you got some cars building up, you got like 5 or 6 cars, and all the other cars are like, okay, I don't know, there's a lot of traffic building up the way. Some other cars are going to go through the 2 stop signs. Okay. And this fraction tells you exactly the proportion. So let's run some numbers. Let's do 1 ohm and 2 ohms. Is what is 2 divided by 1 plus 2? It'll be 2/3. And let's say the current was like 9 amps. What's 2/3 of 9 amps? It'd be 6 amps, wouldn't it? And then if you do 1/3 of 9 amps, that'd be 3 amps. So what I'm saying is, or you guys tell me, right? If I got 9 amps and I got 1 ohm versus 2 ohms, how many amps go through the 1 ohm? 6. And how many amps go through the 2 ohms? 3. Aha, you see it? And then the 6 and the 3 add up to the original 9, and that satisfies the junction rule. You guys good? All right. So, all right. I think that's enough posters today. Let's solve some of these. So I gave you guys a page that looks like this. Now, like usual, my numbers are different than your numbers, but we all have the same geometry circuits. Okay. Now, the direct questions are what's the equivalent resistance, and later on, what's the current flow? And then on the back, I got some Kirchhoff tables. But we are just a little different because we're just a little bit different today. Also have a multimeter ready, so I'm going to bring at least one of these today. We'll do as much as we can with the time we got. So let's do number 3. You guys see number 3? Okay. Now, tell you what, I'm eventually going to pick up this page. So if you want to solve some of these, we go on. That's okay. I'm really just going to fully focus on number 3 for a long time. Right? If you want to take some notes, you can take notes. This is going to all be in your notes if you like. And I'm going to use my own numbers, which are probably different than your numbers. So, or what? Right, so I'm going to draw the circuit. Draw the circuit right here. Okay. And number 3 is very simply a voltage source on the left side. So there's my battery. Okay. And I have 3 resistors. resistor, resistor, resistor. Okay. Now I'm going to name these resistors resistor A, resistor B, and resistor C. I know. Okay. So you guys go with that? Resistor A, B, and C. Okay. And I know this is a voltage source over here. I'll call it delta V for some potential difference. Okay. Now let's tag some numbers to all these. So straight off the page. Now my resistors are 7, 8, and 9 ohms. I just created some random numbers when I made up this page. So I'll just use those. 7 ohms, 8 ohms, and 9 ohms. If you want to use my numbers in your notes, that's fine. If you want to use yours on your page, up to you. Okay. I'm going to add another detail. You guys see this battery over here? I'm going to call this 12 volts. Now that's not on the page. I'm just making that up right now so that I can solve other things later. Okay, you guys good with all that? Okay, we're good. Okay. Now, eventually, I forget if I showed you guys this earlier, but eventually, when I get you guys the lab version, this is a lab page. I've already printed all these out. I'm going to have you guys draw some different circuits. So draw some different schematic diagrams over here. And then within the circuit, you're going to use this multimeter to figure out what are the voltage drops and what's the current at each location. Right. So we'll just do the numerical version of this right now. Right, and I'll do a little bit with the multimeter. You guys can see how this works, right? So let's make one of those big old tables right here. Let's do a 5x5 table. Right. Actually, I got kind of a poster version of this too, so I'll show you guys that. I'm going to make that poster right there. That table, making that table. You guys see it's 1, 2, 3, 4, 5 columns. You guys see that? 5 columns, right? What's the resistance in ohms, the potential difference in volts, the current in amps, and the power in watts, right? At any different location. Okay. And so I'll make that table. You guys can make this table with me. Let's do 5 columns. So we got 1, 2, 3, 4, 5 columns. Right? And also do a bunch of rows. Let's go 1, 2, 3, 4, 5 rows. I think I'll do it for this one. Okay. You guys got a 5x5 grid. Okay. So I'll have different locations. I want to know what's the resistance in ohms, what's the potential difference in volts, what's the current in amps, and what's the power in watts. Okay. Okay. The locations are going to be resistor A, resistor B, resistor C, and the battery. All right, you guys catch up to that. So you guys all write this down? Paper here. It's yeah, right over here. Is all right? The big old table. Okay. Now I know my resistors because I got those off my page. So I'm using my numbers here. I have 7 ohms, 8 ohms, and 9 ohms. Right. I also know the voltage of my battery, which is 12 volts. Now it goes over here in this column because it's volts. So I got 12 volt battery. Okay. So those numbers are given. Right. And that's all you need to fill out the entire table. But it's determinable at this point. What is the voltage drop across each resistor? What's the current flowing? What's the power at each resistor? What's the power supplied by the battery? We can figure all that out. Okay. All right. How you guys doing? Is that right? Is good? Yeah. Oh, I just made that up. Okay. I just made up a 12 volt battery. I'm just doing it for this example. Yeah, go ahead. You think of a whatever volt battery. Yeah. All right. So, first calculation. Let's figure out what's the total equivalent resistance from the point of view of the battery. I'll call it Req, the total equivalent resistance. Because this battery feels like it's pushing against some total resistance. Okay? Now, since these three are all in series, guys, how do you figure out the total equivalent resistance in series? Just add them up. Yeah, resistor A plus resistor B plus resistor C. So for me, that's going to be 7 ohms plus 8 ohms plus 9 ohms. I think it's like 24 ohms. So I have 24 ohms total resistance. It's as if there's a single 24 ohm resistor. So I'll go down to resistance at the point of the battery. I'll call it 24, and then, well, here's the unit is ohms, 24 ohms. There. You guys get there? Good. Since I got a couple numbers for the battery, I'll go ahead and fill out the entire row for the battery. Okay. So maybe you guys can figure this out. How do you guys think? I know it's a lot of new information. How do you guys think I'm going to figure out what is the current supplied by the battery? Does anybody know how to figure that out? The current supplied by the battery? Whose law? Ohm's law. Ohm's law. Yeah. So current is voltage on resistance. Like, you guys know the battery voltage. Okay? I made it 12 volts. You guys know the equivalent resistance that's pushing against. We just found that out by just adding them all the resistors up because they're all in series. You just divide that and figure out how much current's going to flow. That's it. You guys can do that? Let's do that right here. Right here. So, math page out. So, call this Ohm's law. It says current is voltage on resistance. Okay? In this case, I got a 12-volt battery pushing against 24 ohms of resistance. Is that like 0.5 amps? Okay, 0.5 amps. Okay, you guys good? Right, so I'll go down to current in amps. I'll put 0.5. I have half an amp flowing through my circuit. All right, everybody good? Everybody good? Everybody know where I got that from? Ohm's law? Yeah, okay, that's good. Okay. All right, and the final cell for the battery, power. Ooh, how am I going to solve how much power in watts? Not Ohm's law, but whose law? Joule's law. Oh yeah, Joule's law. Hey, we got 3 options. 3 options. I get a current times voltage. I get a current squared times resistance. Voltage squared divided by resistance. Here, I'll do one of these on paper. And yeah, let's start with that. Let's do Joule's law. I'll start with P equals IV. Power is current times voltage. Because I know this. I know I have half an amp of current. So 0.5 amps of current. And I know I have a 12-volt battery. 12 volts battery. Would that give me 6 watts? 6 watts? And so power in watts. That's 6 watts. 6.0. How about that? Okay, so you guys good with how many watts? Okay. Let me try the other methods that I could have done. I should be able to also do either of these and get the same answer. Is that really true? So let's try current squared times resistance. Try that. So current 0.5 amps squared times resistance of 24 ohms. That, hey, it's still 6 watts. Look at that, still 6 watts. And the third way I could have done it is voltage squared divided by resistance. Let's try that method. So try 12 volts, square that, divide by the resistance of 24 ohms. That, hey, it's 6 watts all over again. Oh yeah. So no matter how I apply Joule's law, I'm always getting 6 watts. Right, so you guys good with how many watts? How many watts? Okay. All right. Now it's time to dive into the circuit and figure out exactly what's going on at each resistor. You guys ready for that? Okay. Now, there's more than one way to do this. I'm going to show you guys a kind of a moderately difficult way to actually. This next step will be the most difficult thing we do for this whole table. All right, you guys ready for the most difficult step? All right. Now, one way to do this is to figure out what's the voltage drop at each resistor by applying this rule right here. You guys remember voltage drop is very simply proportional to each resistor on a series setup, right? You guys remember that? Let's try that. Okay, and then I'll show you guys. This is actually an easier way to do it, but I'll show you guys this way first so you can see it works. So I'm saying the voltage drop across resistor A is resistor A compared to the total resistance, A, B, and C, because they're all in series, all multiplied by the voltage from the battery. Okay. So the voltage drop across resistor A is, resistor A is 7 ohms. The total resistance was 24 ohms. And my battery was 12 volts. Well, over 24, it's half, that's 3.5 volts. That's what it works out to. Okay, you guys okay with that? We're good. So to voltage drop across resistor A, I'll put 3.5, and that'd be how many volts? Right? I could also do that for resistor B and resistor C. So resistor B was 8 ohms compared to 24 ohms times 12 volts. That'd be what, 4 volts? So put 4.0 volts right here. Okay. And then resistor C was 9 ohms compared to 24 ohms, 12 volts. Would be 4.5 volts. 4.5 volts. Okay. All right, that okay so far? Is there that? All right. So what I did to find out the voltage drops is I was just applying this rule right here. I'm saying the voltage drop across any resistor, as long as they're all in series, is just proportional to that resistor. Okay. All right, and that so I did an equation for each one of my resistors, A, B, and C. All right. Came out to those values right there. All right. Oh, no, I'll show you guys another way you could also get those same numbers, but I'm working up to that. Okay. Here, let's look at this picture right here. Right? Because isn't this exactly what we're doing? Got 3 resistors in series, right? And if all of this is really true, what do you guys know about if you add up the heights of the 3 waterfalls, what does that always equal? The height of the battery, this pump, right? Isn't that the loop rule? That's the loop rule, isn't it? Right? How many volts up? If you add up all the voltage drops, it has to zero out. Okay. So let's see, did that actually work? Let's find out. So what happens if I add 3.5 volt drop there, plus a 4 volt drop there, plus a 4.5 volt drop there? Check that, right? Because when I hit enter, it's got to add up to what? Does it have to add up to 12 volts? There it is, 12 volts. 12 volts, same thing. You see that? Right. Now, right. You guys want to see an easier way to solve all that? There's an easier way to do it. You guys ready for the easy way? Right. Again, all these circuits are different, so we're just looking at series. Right. Let me ask you guys a different question about series. What do you guys know about the current everywhere for a series circuit? The current is always what? The same everywhere. Yeah, it's always the same everywhere. Hang on a minute. Do you guys know what the current is? It's half an amp. Right? Guys, if the battery is supplying half an amp, is it going to be half an amp everywhere? Right? So does this have to be half an amp, half an amp, half an amp? Wouldn't that be true? Right? But if that's true, oh, so it's like you guys ever solve a Sudoku puzzle? Like if you get some numbers in place, you kind of figure out where other numbers go. Right? But there's not one way to solve it. There's like multiple entry points. Right? This kind of, you think that this way too. Right? Let's go back to Ohm's law. You guys remember current is voltage over resistance? Well, there's another form of Ohm's law that you'll see a lot, which goes like this. Can I cross multiply that resistance? Is that okay? You get V equals IR. Could that also be Ohm's law, just a different form? So I'll also label this Ohm's law. It's just a different way of looking at it. Okay. So if you know current and resistance, you can solve for the voltage that way. Okay. So let's try for any one of these resistors. Like, how about resistor A? If I know there's half an amp of current, let's do half amp of current. And I know 7 ohms of resistance. Isn't that 3.5 volts also? You guys get it? Oh, hey, look at that. That's what we got by digging through the Kirchhoff rules and the proportional voltage drops. You guys see it's the same thing? It's the same thing as what we've got before, right? You could also do that for these next ones. Guys, what's 8 times 0.5? 4. What's 9 times 0.5? 4.5. Right. Yeah, see, you could have done that way. Like if you know the current's the same everywhere, you could just apply Ohm's law and boom, boom, boom. You could have gotten voltage that way. And that would be a lot easier too, wouldn't it? Guess that? Is that? Right. Or alternatively, you could have used my fraction form of Ohm's law and then V over R. Here, let's see if that works. Guess what's 3.5 divided by 7? It's 0.5. What's 4 divided by 8? It's also 0.5. What's 4.5 divided by 9? It's also 0.5. Look at that. So, of course, it always had to be the same current everywhere. I mean, actually, we kind of started from knowing that too. All right, you guys good with all that? We're good? All right, so we got one more column to go. It's power in watts. I think I broke this out a few minutes ago. So you guys know we're just going to do this all over again, right? Let's just do, here, I'm just going to do power is current times voltage. I'll just do this on my calculator screen. Get some numbers. You guys can probably figure out the rest of this. Let's do this. So I'll do current times voltage. So let's do 0.5 amps times 3.5 volts. That gives me 1.75 watts here. It's like joules per second. 0.5 times 4 is 2 watts. And 0.5 amps times 4.5 volts is 2.25 watts. Okay, there's power in watts. Okay. And that is the power in watts is sort of related to how bright the bulb burns, if it's a light bulb. Okay. All right, you guys okay with that? All right, so there's one last check I wanted, because we got the whole table filled, but you guys remember there's multiple ways to solve this and to look at this. So suppose you get to the end, you're like, I'm not 100% sure. Did I make an arithmetic mistake somewhere along the way? I don't know, right? One last check, which goes like this. Do you guys think that the power demanded by the 3 resistors has to be matched by the power supplied by the battery? Does that make sense? Kind of like a supply and demand situation, isn't it? Right? I mean, having all this power and watts supplied, it better be supplied by the battery. So let's see if that's also true. Does supply match demand? Okay, well, it's 1.75 watts plus 2 watts plus 2.25 watts. If I add up all that power demanded, see if you guys are following. Guys, when I hit enter, I am adding these 3 cells right here. What does the answer on my screen have to say if I got the table right? Yeah, it has to, right, exactly. It has to be the 6 watts supplied by the battery. Let's see, is that true? It is. It is 6 watts. Look at there, 6 watts. Right, guys got that? All right, are we good? All right, so let's see, what does this look like? All right. So, all the way. Okay. So I think I may have told you guys, I'm gonna get you guys some breadboards pretty soon, but I was having trouble using the multimeter to measure anything, but I have 3 in series here. There's 3 in parallel. Here's kind of a hybrid setup where eventually work for us. Well, if it's combination both. But I know these Christmas lights work really well. So here's 3 Christmas lights in series. Basically, 3 Christmas lights in series. I also have my cell phone charger, which is at 5 volts direct current, and I have my multimeter. So I did a demo of this yesterday. I'll do a demo today to close out the class, and then I think in a couple of days. Well, I want to get you guys this lab soon. Okay. So you guys ready to see the multimeter again? So let's make sure this lights up. Let's light up. Yep, they're all lighting up. I'm going to throw a binder clip on one of the leads to hold this together. Okay, it looks pretty good right there. Right, binder clip on one lead. Right. Right. Now, if I want to measure voltage, I have to change something on my multimeter. I have to take this plug out, pop it in on the side that says volts. I've changed this toggle. Now, you guys remember anything in the top left corner is volts DC. I'm just moving the decimal around. I mean, I guess this is about 5 volts. Yeah, so put the decimal right there. Okay. Then take the leads of my multimeter, put one on that end. Okay, and then now if I want the voltage across the entire circuit, then I could put the other lead right here. Come on. It's not working for me. Yeah. Try this way, do more direct connection. There it is. You guys see 4.8 volts? Yep, 4.8 volts. Okay. Now, if I do across one resistor, let's just do it across one light bulb. Hey, look at that. You guys see 1.6 volts? Okay, so 1.6 volts drops across one of these. How about across two? This is, hey, look, it's 3 point something, like 3.2 about. So it's like 1.7 volts across one, about 3.2 volts across two, and then about 4.8 volts across all three. You see that? Okay. Okay. So that's voltage. Okay, you guys go with voltage? Okay. Now I still need to show you guys current. So I need to make some changes. Let's pop this up. Pop it down on the other side. So it says amps. I switch this toggle switch to, it's not quite the orange button. It's the one right before that. It says some number of milliamps. I'll always call it amps though. Okay. Okay. I need to break open the circuit. Oh, look, all the bulbs are off. And then connect the black lead to the black and the red back to the circuit. You guys see how I'm going to force the current to flow through the multimeter? As soon as I connect it, it will. And the bulbs will turn back on. There it is. You guys see the bulbs turn back on? Bulbs are off. Bulbs are on. Right. And guys, look at the screen on the multimeter. What does it say? 1.3? Because that's 1.3 what? What is that? What's the unit? 1.3. What am I measuring? Current? What's current measured in? Amps. Guys, that's 1.3 amps. You guys see 1.3 amps? There you go. Okay. Okay. So just I'm connecting the multimeter, the ammeter function in series to make that happen. All right. So yeah, we're about out of time, but I think tomorrow I want to do as many examples as I can with you guys, and then get you guys to the lab when I'm able to. So we'll stop the recording right there.